You know what? Today, that is true. Y'all are good. Graded your exams. And as a class, y'all did much better this time. So, yep. Well, was I one of them? Oh, okay. Huh? Of course I took it. I take every test before I give it to you. I made 100, and I made 100 in like 15 minutes. Well, I do kind of know the answers, because I'm the one that made up the test. No, I have to do that, so I can have an answer key to grade everybody else's work with, but I also have to make sure that I'm not giving you a test that's going to take you 3 hours to finish. Well, it generally will take the student longer to complete a test that the teacher can take. So if it takes me more than 15 minutes to do a test, then I cut part of it out or do something to get it down. Otherwise, and there'll be some people in the class who will sit down and they'll go, yep, zip, 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 and they're done. And maybe not in 15 minutes, but maybe in 15 minutes or 20 or 30. But anyway, this is last hour. So where's my not graded assignments? Go right in here. And your graded assignments right in here. Yeah, overall, y'all did much better. So, well, that depends on the individual. Ryan McGee. Caleb Collison. Callison. Hold up your hand. There you are. Hunter Turnage. Now, I do want to point something out to you. On question number 5, there was a typo that snuck in there. That was not supposed to be 6.1 times 10 to the power of 30. That was supposed to be 6.1 times 10 to the power of minus 30, which drastically changed the results. Point is that, R.J. Darnell. Point is that the question then became so ridiculous that I just did not count it. What I did do was, for any of you who worked it correctly with the wrong number and got the right answers with the wrong number, I kind of gave that to you as a bonus point to help boost you up a little bit. Those of you who looked at it and just said, wait, what? I just deleted it off the test. So nobody got penalized for question number 5. Dwayne Lee. Cash. As in all others pay?
Yeah.
Colton Mashburn. Oh, there we go. Do you get the reference? Jacob Bettis. It's a popular sign. In God we trust, all others pay cash. Evan Beecham. Chad Pryor. And Dylan Anderson. Hoorah. All right. Let's see, Dwayne Lee. Colton Mashburn. Cash Dowers. Jacob Vettis, Chad Pryor, Caleb Callison. You?
Yeah.
Hunter Turnage, Evan Beecham, and Colton Mashman. There you go. All right. Stick these back in the assignments graded folder so I can hand them out next time. I guess the place to start this morning is, does anyone have any questions from the homework? We definitely seem to be hitting the part of the material that you're all most familiar with, so. Everybody, does anybody want to go over any of the exam questions or any of the homework from before? Number 24 in the. Let's see. Okay, that would be back here a ways. Okay, what page is it on? Oh, okay. I'm sorry, I was looking in the wrong chapter. The length of aluminum wire is connected to a precision 10.00 volt power supply. And a current of 0.4212 amps is precisely measured at 23.5 degrees C. Wire is placed in a new environment of unknown temperature where the measured current is 0.3818 amps. What is the unknown temperature? All right. Let's start with our knowns. 10.00 volts. And that means we've got how many significant digits there? 4. Remember, when you start adding zeros past the decimal point, you're increasing the precision. These are no longer just placeholders telling you where the decimal point is. If we didn't have these, if it was just 10 volts, then that would only be technically one significant digit. Okay, but by adding them past the zero, you're increasing precision. Okay. Current. 0.4212 amps. And the temperature is 23.5 degrees C. And what is the wire made out of? Aluminum. Okay. So we go back and find the table that gives us the resistivities and the temperature coefficients. In aluminum, we get 2.65 times 10 to the minus 8. Ohms, ohm meters. And the temperature coefficient, okay, that's, we call that what, alpha? Yeah. Uh, 0.00429. Now, what's the maximum number of significant digits we can have in our final result? 3. We've got 3 significant digits here, and because these zeros only tell us where the decimal point is, they don't give us any added precision. So we actually only have 3 significant digits here. Right? Now I'll go back and find the problem. And it doesn't tell us how long the wire is, but we can determine that if we need to. How would we determine that if we needed to? Or actually, could we? You would need the area too. What we can determine is the total resistance of the wire. Yep. So what is our resistance? Right? Yeah, that's right. So we've got and what does that give us for our resistance? Our precision 4 significant digits resistance. $23.74. 4 significant digits. 4 here, so we keep all 4. And in general, this is just general good practice when you're solving, when you're doing work, whether you're working for real in the field or in homework exercise, keep all those extra digits, and then wait until you get your final answer to round it down to the number of significant digits that are justified. You'll generally get a better result. Okay. That is the resistance of this length of wire at 23.5 degrees C. Is this thing vibrating at me? Oh, for crying out loud. Turn this stupid thing off. Yes, off. Hope we don't get an active shooter on campus during class. That's why I have to carry the stupid thing, so if they send out alerts for weather or anything, I can get it. Great. The only thing I hate worse than one of your phones interrupting the class is when somebody I know that presumes to interrupt my class for me. Now, this is the resistance at this temperature, 23.5 degrees C. Now, what do we know? That when it's placed at a different temperature, the measured current is now 0.3818. I at the second temperature is 0.3818. I'm asking, yeah, 0.3818. Okay. So the current went down, which means the resistance went up. What does that tell us about the temperature? Does the resistance go up or down with increasing temperature? Higher the temperature, the higher the resistance. Have you ever noticed when, and I know they don't really have incandescent bulbs anymore, but you're all old enough to remember incandescent bulbs. Did you ever notice how they always seem to burn out right when you flip the switch on? Because at that point, the filament is still at room temperature. The actual current, the wattage, all of that the thing is designed to operate at, the design is for it to operate at that point with that much power and that much wattage, that much luminosity, whatever, at temperature. So as the temperature goes up, the resistance goes up and the current comes down. Whenever it's still at room temperature, the resistance is lower, which is why you get that initial surge of current before it has a chance to warm up. And that's why they typically fail when you first turn them on. All right. So, now they want to know what is the new temperature that would cause that aluminum wire to increase in resistance. So what do we need to know? What has changed? Has anything other than the new resistance changed? The temperature has changed. The resistance has changed. The current has changed. Has the voltage changed? So we know that the new resistance, the new temperature, still has 10 volts. The current is now so what does that tell us the new resistance is at the higher temperature? Or at okay. Well, we got our temperature coefficient. Where's the equation in the book? That's what I'm trying to, I don't want to try and write it from memory and mess y'all up. There it is. Rho at temperature is rho at 1 plus alpha times T minus T naught. So we're going to look for the rho, the resistivity, now, how does resistivity relate to resistance? Did I get that right? Say again? Yeah, rho is L over A. So, did length and area, did that change? Maybe a little from heat expansion, but we're going to pretend like no, it didn't. We're going to say it's negligible. Actually, that's, I think I made that point back when we did the electric dipole moment, that it's tempting to, when things change in a very small amount, it's very tempting usually to say, well, it's negligible, we'll just ignore it. But it isn't always justifiable to do so. When does it become justifiable? It ties into significant digits. If the change in length only happens out in the 8th or 9th decimal place, how much is it going to impact our measurement? We're only measuring four significant digits. So something that only changes in the 8th digit is not going to change our measured results. And that is when you can legitimately say that doesn't change, or that the change is negligible. Okay? And I'm trying to stress this for each of you, because you're going to find that a lot of mathematicians love to wave their hands and say, oh, well, we can show this, or we know this, or this makes sense, or this is intuitively obvious, and they wave their hands, but they don't actually prove anything. One phrase you're going to hear a lot, or maybe you'll hear a lot, is when someone says, this is a statistically significant result. Well, what exactly does that mean? How do you quantify a statistically significant result? And the fact is, they don't. That's part of hand waving. Okay? This can become the same kind of hand waving crutch for engineers and technicians. You do not have to let it. There is a quantifiable way to determine whether or not you need to worry about this variable changing or not. And that has to do with your significant digits. So, anyway, enough of that. This is constant. That means rho is within a multiplicative constant of resistance. So if we measure, if rho changes by X amount, times length over area, then we know that this is all equal to what it was, so this X is also going to linearly affect the resistance of the same amount. Okay? Because this is a constant. So now when we solve for this, how much rho changes, we also resolve how much resistance changes. So, how would we solve for rho at temperature? Let's see. And we know T sub naught was 23.5 degrees. We've got alpha and rho sub naught. How do we, someone want to do that and turn that into a proper number? Alpha is 0.00429. Rho sub naught is 2.65 times 10 to the minus 8. And 23.5. Wow. How many is it? 1, 2, 3, 4, 5, 6. That. Can we find rho at temperature? I mean, just from what we know, without going through all this. We don't really know give me a minute here. I'm looking to see if I'm going down a long way around to get there, that we might be able to get there shorter. Actually, we can, because we know that from this equation here, we know this resistance, and no, rho sub naught is specified at 20 degrees C, not 23 degrees C, so we can't. Yeah, this is. This is actually turning into a bit of a head scratcher, isn't it? Anybody got any idea on how to proceed? Huh? I don't know what that means. No, seriously, what is Chegg it? I don't know what is Chegg. Is it like an app? Oh. Yeah, well, let's not do that. Yeah, let's say again. This is actually, there seems to be something that I'm not noticing. Did I miss something in the definition of the problem? Well, alpha Yeah. And I just gave a big long speech about it, and then I completely neglected it. Resistance is within a multiplicative constant. This is all this is just how much does it change? The initial resistance plus this much change in that resistance times this many degrees C. Look at the units of alpha. What are the units of alpha? 1 over degrees C. So when you multiply alpha by some number of degrees C, you get a net change. You get 1 plus that much change in the, this is just a scalar. So instead of writing this as rho and looking for the new rho, since we know that our length over area is going to be constant within the realm of our problem, then we can rewrite this equation as resistance at temperature is equal to the initial resistance times 1 plus alpha change in temperature, which is all this is. T minus T sub naught is change in temperature. So how would you solve for the change in temperature? Well, R at temperature, we calculated that as what? Did we calculate the resistance at the temperature? 26.19 ohms. Is equal to, what's the initial resistance? 23.74 ohms. Times 1 plus alpha delta T. What's the ratio? If we divide both sides by the 2374, what's that give us? It's a new number here. .103. 1, 2, 3, 4 significant digits. 1.104. Okay. And that is equal to 1 plus alpha delta T. Well, if we subtract 1 from both sides, we get 0.103 is equal to alpha delta T. And we know alpha, 0.00429. So 0.103 divided by 0.00429, which now we have 3 significant digits, is equal to delta T. What's this ratio? .01. Okay, so that would be 24.0 degrees to 3 decimal places. And that's equal to delta T. Well, start over here. 24.0 is equal to delta T, which is what? T minus T sub naught. And T sub naught is, what was the initial temperature? 23.5 degrees C. So add 23.5 to both sides and you get your final temperature of 47.5 degrees C. Check it out. The book almost stumped me. How did you do it?
I just replaced the override and plug it in.
Show me what, say again?
So you got the arm,
Right here? Okay, and you did what? Oh, okay. Well, V over I and R are the same thing. So that shouldn't change anything. The question is, how do you justify putting R in? And in order to do that, this has to be constant. Okay, because if length and area are changing with thermal expansion enough to make that not constant anymore, then you can't ignore that. All right, any more questions from the homework? Hopefully nothing that complicated again. No more questions, and we'll get back to the lesson. We've looked at power. Oh, here's one they were talking about. We were just talking about this, that the light bulbs, when they're at the rated power is for when they are at temperature. They use an example here of headlights. We talked about, it just sort of came up earlier that there really aren't any incandescent light bulbs around anymore. Well, I know a lot of people stockpiled them and stuff, and we're not going to go off into the politics of federal overreach and regulatory burdens and the rest of that, because that's not what we're here to study. But what was the reasoning behind getting rid of incandescent bulbs? They're not efficient, but what does that mean? What's the purpose and function of a light bulb? To generate light. But incandescent light bulbs, about 90% of the energy they consume was not converted into light, it was converted into heat. That's why you couldn't just go in and change a burned out light bulb without getting a rag to hold it with. What happens when you turn on a light bulb? You put power into a light bulb. Electrons start flowing through that wire. They start flowing with some kinetic energy. And every time one of them hits one of those ions or one of those molecules or atoms in whatever the filament is made out of, it imparts some of that kinetic energy into that atom. And that atom then starts vibrating within within the matrix of its substance. You know, it's a solid, so somehow it's kind of fixed in position. Most metals, it's kind of a crystalline structure. The point is, it's not going to go anywhere easily. And if it does, that generally means you've let the smoke out. But when the electrons hit it, they're going to impart their kinetic energy to it. And that means it's going to turn into vibration, vibratory motion of that atom in that position in the matrix. Wow, that means something completely different now that Keanu Reeves made that movie. In the structure of the metal, the atoms, the more they get bombarded by these electrons moving through, the more they vibrate. And that vibration is heat. It's energy that's being radiated out because that filament wants to go back to ground temperature. It wants to go back to equilibrium, to temperature with the room around it. So it's going to radiate out that heat into the air around it or into space. It'll either be, it'll give it off through conduction or convection or just radiation, but it's going to try to get rid of that extra heat. Sometimes as an engineer or a designer, you're going to have to help it out by giving it a heat sink, something that'll provide an efficient means for it to give up that extra heat. But anytime you have an electric current flowing through a device, it's going to be generating heat. Sometimes it's negligible and you don't have to worry about it. Other times you have to take measures to protect against it, to help it get rid of it. But it's always going to generate heat. And with incandescent light bulbs, most of the energy that they dissipated was dissipated in the form of heat radiating out into the room around it. Matter of fact, years ago, people actually used incandescent light bulbs as heating elements to keep, to put some heat in the dog's house outside on cold winter nights, or to incubate eggs when they were trying to hatch quail or chicken or ducks or whatever, snakes, birds, lizards. Fluorescent lights don't do that. Fluorescent lights don't generate that much heat. You take a fluorescent light while it's burning bright, been burning for hours, grab it with your bare hand, twist it, take it out of a socket, no problem. Why is that? Someone say it out loud. Yeah, they're more efficient. They don't generate most of the energy that goes into a fluorescent tube ends up being converted into visible light. Or anybody know? It's actually going into producing UV light. And UV light is starting to get up into the spectrum of what they call ionizing radiation. And if y'all are going to work in industry, then eventually you're going to learn all about ionizing radiation. It's basically at 150 nanometers, a photon has enough energy to ionize water. And that's what's called ionizing radiation. And since your body is mostly water, that's the threshold that they choose for deciding that, okay, this photon is starting to get to a realm where it could become health hazardous. Might be able to start causing, you have to worry about, can it cause cancer or tumors or things like that. Well, fluorescent bulbs, the way they work is they produce UV radiation, not visible light. The visible light that you see coming from a fluorescent tube is from the phosphor coating inside the tube. It's giving off visible light photons every time it gets hit with a UV photon. So the mercury vapor in the bulb is excited, produces UV light, which hits the phosphor coating, which in turn turns it into visible light. Overall, it's much more efficient than the incandescent bulb. Then, of course, we get to LED bulbs, and those are just remarkably efficient compared to any of the other light bulbs before them, because they only produce the light that you're trying to produce. And the heat, You know, you can't not have heat generation if you have electric current, but it's minimal. It's truly getting down to the negligible stage. Not all of them. Some of them they have to put significant heat sink backplanes on them. Okay, how many of you have an LED television at home? How many of you have I have a 65-inch big smart TV at home. I turn that thing on and leave it on for a little while. You can feel the heat radiating off of it when you walk past it. So even LEDs, you know, even though the individual LED doesn't produce much heat, you put a few bajillion of them on one panel, and you better put a heat sink on the back of it too. Okay, well, I do want to say this. I do want to cover a little bit out of power. We talked about power, voltage times current. I don't know, have y'all actually read the book? I do want to show y'all this because I want you all, I don't know if you've all read the book. If you have, then this may be old hat to you, may be boring, but if you haven't, I want you to pay attention to the fact that the power, when we talk about power with regard to components in electric circuits, what are we saying? We're talking about how much energy that circuit dissipates per unit time. Okay? You have a resistor in a circuit, you've got current going through it, there's a voltage developed across it. That means that it is dissipating a certain amount of energy, so many joules per second. That's what we call watts. But it's energy transformed per unit time. Well, what's the energy? Joules. It's the amount of charge times voltage. The charge of remember EV? The EV units, that was energy. It's charge per volt, or charge times voltage, gives you energy. Joules per unit time. Charge times voltage over time gives you joules per second. But what? Think back to our definitions. What is it? What is it called when you have so much charge per unit time? Anybody? Okay. Pop quiz. Who can tell me what that number signifies? No, that's the number of electrons in 1 coulomb of charge. This is number of electrons, or just E, per coulomb. The number you're thinking of is 1.6022 times 10 to the minus 19 coulombs per E. It's the reciprocal of this number. This is how many electrons there are in 1 coulomb of charge. This is how many coulombs of charge there is in 1 electron. And when you have 6.24 times 10 to the 18 electrons flowing past a point in the wire every second, you have amps. You have current. That Q over T is equal to current. And that's where we get the equation power equals current times voltage. That's how much energy is being dissipated in that voltage. Wherever this voltage is being dropped across, that's how much power is being dissipated, is being converted into something, into light, into heat. But it is dissipating that much energy per second, that many watts or joules per second. And yeah, I see time is up. So I did want to tell y'all that if I didn't tell you, that this last exam was a dramatic improvement over the first one. So whatever y'all been doing different, keep it up.
Down.